Hello, I am Ahmad, and in this video we are going to talk about detailing chapter 9 of Eurocode 1992-11. Apart from designing of the reinforcement in one element, it can be a beam, it can be a column, it can be slab. We need to check the minimum requirements of the element. For example, when you have a moderate length of the beam and you put the dimension in a way that when you calculate, you will see that the reinforcement that is designed is relatively small and you don't need that much reinforcement. But on the other hand, we need to have a minimum value of reinforcement. Also, the spacing of the reinforcement is also limited to some regulations in every code. In Eurocode also, we will check through this video. The first step for a design of a concrete element is to have a simple dimension. For example, you want to have a 6 meters beam, and then you need to know what is the required depth of the beam. So that is not given in chapter 9, it is given in chapter 7, and the minimum requirement in this chapter is due to serviceability and, for example, checking the deflection. For checking the deflection, as we know, the concrete has a different behavior compared to a steel, for example. In a steel, you have a constant homogeneous cross-section, which the moment of inertia is the same, and also the modulus of elasticity is constant. As a result, you can calculate the deflection easily by elastic equations. But in concrete, we know that the moment of inertia and the neutral axis would be different depending on what is the moment on the element. For that reason, when you want to check the deflection, you will see that the deflection might be different than elastic equations because the moment of inertia is changing from the beginning to the end of the element. For that reason, calculation of deflection of a concrete beam or concrete slab might be as simple as in that regard. Many codes, including Eurocode, is suggesting if you have a certain length towards the depth ratio, then you can say that, okay, in this case, we can ignore the deflection calculation. So let's start from that point. In clause 7.4 of Eurocode, we can see that it's deflection control. 7.4.1 general considerations: the deformation of a member or a structure shall not be such that it adversely affects its proper functioning or appearance. Number 2, appropriate limiting values of deflection taking into account the nature of the structure, of the finishes, partitions and fixings, and upon the function of the structure should be established. And number 3, deformations should not exceed those that can be accommodated by other connected elements such as partitions, glazing, cladding, services, or finishes. In some cases, limitation may be required to ensure the proper functioning of machinery or apparatus supported by the structure or to avoid ponding on flat roofs. So, and also other clauses would address to the limitation of L divided by 250, 500. You can check by yourself from Eurocode. In clause 742, on the other hand, we can see that cases where calculations may be omitted. Generally, it is not necessary to calculate the deflections explicitly, as simple rules, for example, limits to a span to depth ratio may be formulated, which will be adequate for avoiding deflection problems in normal circumstances. More rigorous checks are necessary for members while lie outside such limits, or where deflection limits other than those implicit in simplified methods are appropriate. So if you check the span to the ratio, to the depth ratio, and it has a sufficient value, then you can ignore the deflection calculation. For this, there is a table 7.4n, basic ratios of span to effective depth for reinforced concrete members without axial compression. There are also two equations in this clause of Eurocode that you can calculate exactly what is span divided by effective depth ratio. That I will cover it later in advanced courses and also in advanced videos. For this time, that is fine if we continue with this table. A structural system, simply supported beam, one or two-way spanning simply supported slabs. It refers to the elements that practically the moment is considered to be zero at both ends. It can be a one-way slab, two-way slab, or a simply supported beam. So typically the ideal element for this case is this type. The next one is end span of continuous beams or one-way continuous slab or two-way spanning slab continuous over one line side. So it's referring to the elements that at one side they are with zero bending moment and the other side they are with non-zero bending moment. The ideal case for this condition is this type of beam. It can be over the supports. So here we can see that at point A, moment is 0, and at point B, moment is not 0. So this is called end span. The other one is interior span of beam or one-way or two-way spanning a slab. It means that we are in the middle of the supports. As a result, both ends are taking some moments. Moment is not 0 in this case. The ideal beam in this case is like a fixed supported beam. Here you can see that at both ends we have moment and moment is not 0. A slab supported on columns without beams. It's very clear if we have slabs connected to or supported on columns without any beams, then we can use that one, and the other one is cantilever. And here we can see we have two columns, concrete highly stressed, or rho is 1.5% and the other one is rho equals to 0.5%. This table is provided for a certain class of concrete, C30, and also with the value of the stress inside the reinforcement in tension is 310 megapascal. So if you want to calculate accurately, then you need to check with the equations given in this chapter. So here we can see the values for highly stressed and the other one is for lightly stressed. One is with rho equals to 1.5%, the other one is rho equals to 0.5%, and this is L over effective depth. And it should be less than 14, for example, or it should be less than 20, depending on the ratio of reinforcement. Then we can calculate what is the required depth as the minimum value. So we can see that the more reinforcement we have, the more depth we need for the concrete element. This is the first step to determine what is the required depth of the concrete, and after that we can go directly to the detailing chapter, which is coming in chapter 9 of Eurocode 2. Section 9, detailing of members and particular rules. General, the requirements for safety, serviceability, and durability are satisfied by following the rules given in this section in addition to the general rules given elsewhere. It means that you need to design the required reinforcement that we need for one element. And then you need to check if the design reinforcement is complied with the detailing rules given in this chapter. The important part is that if we have sufficient reinforcement and it is placed correctly in the proper position, then we can increase the lifespan of the concrete element. The detailing of members should be consistent with the design models adopted. Minimum areas of reinforcement are given in order to prevent a brittle failure, wide cracks, and also to resist forces arising from restraint action. The rules given in this section are mainly applicable to reinforced concrete buildings. So the code is for buildings. For a special case, we need to follow other regulations. 9211, minimum and maximum reinforcement areas. The area of longitudinal tension reinforcement should not be taken as less than AS minimum. See also 73 for area of longitudinal tension reinforcement to control cracking. So for crack also we need to design. The crack calculation video will come later Note 2, the value of AS minimum for beams for use in a country may be found in its national annex. The recommended value is given in the following: 0.26 FCTM divided by FYK BT times D, but not less than 0.0013 BTD. For those who are writing the code or a spreadsheet to calculate, AS minimum is always the maximum value of 0.26 FCTM divided by FYK times BT times D and 0.0013 BT times D. BT is the mean width of the tension zone. For a T-beam with the flange in compression, only the width of the web is taken into account in calculating the value of BT. FCTM can be found in the table 3.1, and from here we can calculate AS minimum. AS maximum also is limited in Eurocode, and the value is 4% of the area of the element. However, in national annex, for example, in Finnish national annex, we can see that AS maximum is not limited to any value. Typically, the percentage of reinforcement is not reaching to that 4% if the design is ordinary and the element is under typical values. And in this video, I'm going to go through the slab and calculation of the requirement distance between the bars. So for that, you can go through the clause 9.3. Before than this 9.3, there are plenty of information in Eurocode that you can follow and find out the most relevant section to your task. For solid slabs, this section applies to one-way and two-way solid slabs for which B and L effective are not less than 5H. H is the thickness and L effective is the effective length between the face of the column to the other column. For flexural reinforcement or bending reinforcement, we need to design the reinforcement according to ULS, but when we calculate them, we need to follow the requirement in this chapter. For the minimum and maximum steel percentages in the main direction, 9 to 111 and 3 apply. So this is referring to, for example, here 9 to 111 and 3 is the maximum. Number 2, secondary transverse reinforcement of not less than 20% of the principal reinforcement should be provided in one-way slabs in areas near supports. Transverse reinforcement to principal top bars is not necessary when there is no transverse bending moment. And also the spacing is limited in Eurocode for the slabs. That is coming in the next clause. The spacing of bars should not exceed S-max slabs. The value of S-max slabs for use in a country may be found in its national annex. The recommended value is for principal reinforcement 3H and 400 mm, whichever is smaller. H is the total depth of the slab, and for secondary reinforcement 3.5H but less than 450 mm. In areas with concentrated loads or areas of maximum moment, those provisions become respectively to 2H and 250 and 3H and 400 mm. So if you have a maximum moment, then you need to decrease this S-max. So to understand better these clauses, it's better if we go through one numerical example. Assume that we have a long slab and the width of the slab is going to be 3.5 meters. And the L is far bigger than 3.5 meters. As far as the length is quite long compared to the width, we know that the behavior of this slab is one-way slab. Perhaps we have the beams or supports in both sides of this slab, one here and the other one in the other side. And usually we assume that if the slab is not continuously over the several beams, we can assume that the support is a simply support. In this case, the direction of the load transfer is in width direction. Please note that if we are designing for a floor, hollow core slabs are long, but they are transferring the load in their longitudinal direction. But if we are pouring the concrete over two beams and it's very long, then the transfer direction of the load is in the width direction. As a result, for designing the reinforcement, we need to design the reinforcement in the loading direction, which is in this case in the direction of green arrow. So then these are the designed reinforcement, which are called primary reinforcement. Also, we need to have the minimum reinforcement in the other direction. These are not designed for any load, and they are called secondary reinforcement. As far as the primary reinforcement is designed for taking the load, it is better if we put them below the secondary reinforcement, because in that case we have greater effective depth. As a result, we have greater capacity for the element. So if we look at the section of this slab, the primary reinforcement is below the secondary reinforcement. Here we can see that we are increasing the capacity by increasing the effective depth. So now the first question is, what is the required depth? Please notice that we are not designing, we are just going through the detailing. Later on we will design what is the required reinforcement in the concrete slab. But this is just for the detailing. Let's have some assumption. C3037 is the concrete, FYK 500 megapascal, and also nothing else. Yes, for the primary reinforcement, B equals to 16, and for secondary reinforcement, we can use 12 millimeter. Usually primary reinforcement in slabs are 16 and the secondary are 12 millimeter. And assume that C nominal in this case is going to be 25 millimeter. According to exposure class, we had another video how to calculate what is the required C nominal. So now, first of all, we need to check what is the required depth. As far as it's simply supported in both sides, then this is our structural system. And if you want to be conservative, for now we can go with highly stressed, rho equals to 1.5%. As a result, L over D should be less than 14. If the length is 3.5 meters, then D should be greater than 3500 divided by 14. It's 250 millimeter. This is the effective depth. We need to calculate what is the required height. So this is up to the middle of the bottom reinforcement, which is 16 millimeter. Now we need to calculate what is this distance. We call it D prime. D prime is the C nominal plus half of B, and you can consider 10% for the ribs of the reinforcement, 25 plus half of 16 times 1.1. 25 plus 8, 1.1, it's 33.8. As a result, the total depth, H minimum, is D plus D prime, which is 283.8 millimeter. We can see that the determined height is not practically applicable. 283 millimeter is not something that can be done in reality. So we round it to the next 50 millimeter. So we take 300 millimeter for the height. This is the first step. Then you can design how many reinforcement do we need. In this case, we are not going to design. We are just checking what is the minimum value of reinforcement. After that, we need to check and calculate what is the minimum reinforcement. For this, we need to calculate what is FCTM, which is coming from table 3.1. So from the concrete class, which is C3037, we can find out FCTM, and it's 2.9 megapascal. Then we can calculate AS minimum, which is the maximum of, as far as B and D are the same, I will write it down 0.26 FCTM FYK, and 0.26 multiplied by 2.9 divided by 500, 0.0015, and 0.0013 times BD. As a result, AS minimum will be 0.0015 times B times D. From this H calculation earlier that we adjusted to be 300, we can calculate D, which is H minus D prime. So 300 minus 34, almost 266 millimeter. For the slabs, usually you do not have the width, and you design the slab reinforcement for 1 meter width. It means that it doesn't matter what is the length of the a slab. You assume that you are talking about only one ribbon here, which the width is 1 meter. So everything is designed for 1 meter, then we give the spacing. So as a result, B is always 1000 millimeter in slabs, and this is 266 millimeter. So then this value will be 266. So it is 399 square millimeter. But instead of writing a square millimeter, we write it down always millimeter square divided by meter. It means that in every meter, we need about 400 square millimeter of reinforcement. Now for the primary reinforcement, we need AS minimum is 400 square millimeter divided by in every meter. And we are using T16. 1 T16 is pi 16 square divided by 4, which is 200 square millimeter. So now if we want to have 400 square millimeter in every meter, then we need to use 2. So if the numbers are not like this time, it is better to write down that N, the number of reinforcement in 1 meter, is 400 square millimeter per meter divided by 200 square millimeter for 1 T16. So then we can see that we need 2 T16 per meter. So it means that you need 2 reinforcement in every meter. And usually we calculate the spacing by dividing 1000 millimeter divided by the number that we calculated, 2 T16. So it will be 500 millimeter. So up to here, fulfilling the minimum reinforcement, we can use T16 every 500 millimeter. But this is not the end of the story. We need to calculate how many reinforcement we need according to the given load. As I mentioned, this is not about the designing of reinforcement. This is about the detailing of reinforcement. And also there is the regulation for the spacing. So here the spacing for the primary reinforcement needs to be less than the minimum value of 3 times H and 400 millimeter. H in this case, we considered H to be 300 millimeter as a result. So it should be less than 400 millimeter. We can see that it is not, and it should be less than 500 millimeter. Also, if we have a concentrated load or we have maximum bending moment, then we need to limit this S to be less than minimum of 2H and 250 millimeter. In this case, H is 300, it will be 250 millimeter. As a result, for that part, we need to limit the spacing to 250 millimeter. In other words, if we want to sketch our slab, the primary reinforcement needs to be E16 every 400 millimeter at max. And here we can see that the bending moment is maximum in the center. In that position, we need to increase the number of reinforcement. So you can easily add 1 reinforcement between every reinforcement, and they do not need to be extended to the end. Usually you might go with the conservative values. So this is E16 every 250 millimeter. So this is for the primary reinforcement. We need to calculate what is the required secondary reinforcement. It's coming from the other rules and other clauses. From here we can see that in clause 9311, item 2, secondary transverse reinforcement of not less than 20% of the principal reinforcement should be provided in one-way slab. So the primary reinforcement is T16 in 200 millimeter, and secondary transverse reinforcement should be greater than 20% of principal reinforcement. So first we need to calculate the area of primary reinforcement, which is 1000 millimeter divided by 200 millimeter. This is the numbers every 1 meter times pi 16 square divided by 4. So it will be about 1000 square millimeter, and usually we write it as millimeter square divided by meter. So 20% of this value, 20% of AS primary will be 200 square millimeter per meter. We have to notice that this value should be always greater than AS minimum. So it should be greater than AS minimum. In this example, we calculated and it was 399 square millimeter per meter. As a result, secondary reinforcement will be 399 square millimeter per meter. In this example, 399 is dominant as far as we didn't design any reinforcement. But for example, if you design reinforcement according to the load, then perhaps 20% of that can cover AS minimum. But in any case, we need to check which one is the required minimum reinforcement. So 399, as far as this is secondary, usually the diameter is different from the primary. 16 millimeter for the primary and 12 millimeter for secondary is quite reasonable. So the 12 number of reinforcement will be 399 square millimeter per meter divided by pi 12 millimeter square divided by 4. So it will be 399 divided by pi 12 square divided by 4, and it's 3.52 per meter. So spacing will be 1000 millimeter. We want to see what is the spacing divided by 3.52. So it will be 283 millimeter the spacing of reinforcement. We round it to a practical value, for example 250. As a result, the secondary reinforcement will be E12 at sign 250. So it means that every 250 millimeter we need to use one reinforcement of 12 millimeter. Then we need to check the spacing to follow the regulation. So in the item 3 of the relevant clause, the spacing of bars should not exceed S max slab, and for the secondary reinforcement here we can find out it should be less than 3.5 H and 450 millimeters. So S should be less than minimum of 3.5 times 300 millimeter and 450 millimeter, which is 450 millimeter. And also in the place that we have concentrated load or maximum moment, S should be less than minimum of 3 times H and 400 millimeter, which in this case is 400 millimeter. To make it easier, we go with the minimum value. So for secondary reinforcement, the maximum spacing is 400 millimeter. Coming back to here, so S max we calculated and it was 400 millimeter. So then the design or the detailing is satisfactory and we can use E12 every 250 millimeter. If it was, for example, 450 millimeter, then we had to limit it to 400 millimeter. It should be noted that if you are designing according to a specific national annex, always check the national annex. For example, in Finland, if we are going to follow the same clause and compare it to what we have in Eurocode, here we can see that we have the same for principal reinforcement 3H and 400. For areas concentrated loads and maximum moment we have the same. The only difference is that here the secondary reinforcement for general design is limited to 4H and 600 millimeter. That is very important, especially if it is limited. In this case, it is not limited less than what is given in Eurocode, but if it is limited to a smaller value for spacing, then we need to follow the specific national annex. So in this example, we can see that the detailing or the minimum requirement for a 3.5 meters width of a one-way slab for the longitudinal reinforcement is T16 every 200 millimeter. And for the other direction, it is limited to T12 every 250 millimeter. And that's the design. And usually you have to sketch also the cross section of this slab to show the reinforcement with the section in your detailing layout. Apart from these two net in the bottom, we need to follow also the minimum reinforcement on the top, and you can design it for the other side and report it in the drawing. That's the end of this example. In this example, we went through the detailing briefly, not the whole story of chapter 9 of Eurocode 2. We went through one example about the calculation of what is the minimum depth of a slab, one-way slab, and then we determine what is the minimum requirement for the spacing of reinforcement. Later on, we will go through the calculation of reinforcement that we need for the design. Thank you for watching. See you next time. Bye.